Hello everyone, I am Sang-tae Kim, Marketing Team Manager of FunctionBay. In this presentation, I am introducing how to optimize dynamic mechanism using CAE, especially multi-body dynamics. This presentation will focus on the practices to select the design variables, objective functions, and constraints with variable examples. First, let's review some background information about optimization. Before I talk about optimization, I'd like to talk about what design is, because optimization is usually referred to as design optimization. When we design something, we first come up with various concepts, which can include many options such as functions, dimensions, capacity, materials, shapes, and so on. Eventually, we will need to decide on or choose one of the several options. In other words, for successful product development, engineers must make choices. For example, let's assume that we need to develop a buggy car. To develop a buggy car, there are several requirements. Therefore, design is the process of making reasonable choices that can meet the requirements of the product. Then, what is optimization? Optimization is the process of making the most reasonable choice that meets the requirements. There are several kinds of theories about optimization, and many of these theories are very mathematical and difficult. Because of this, it causes many people to think that the optimization process itself is also difficult. This presentation is not about optimization theory. What I'd like to present here is that anyone can do optimization using CAE without having a deep knowledge about optimization. In fact, we often follow this process of making reasonable choices and then going further by choosing the most reasonable choice in our daily lives. So, don't be afraid of optimization. I described earlier that optimization is the most reasonable choice. In order to do optimization, three factors are required. They are design variables, objective functions, and constraints. Design variables are the inputs we can choose to achieve the goal. In this image, the path determined by the x, y, and z coordinates to go somewhere are the design variables. Objective function is the goal to be achieved. In this case, it is the destination. For example, going to the highest point, going to the lowest point, or going to the point whose slope is the steepest. Sometimes, there can be multiple objective functions, such as going to the highest point and arriving there as soon as possible. Constraints are the conditions that are to be met when achieving the goal. For example, the puddles or the residential area must be avoided, or that a specific point must be included in the path. These are constraints. Let's look at some daily optimization problems that we may experience. The cost of a meal, transportation to and from work, or daily exercise are a few examples. When you look at a restaurant menu, we consider taste, how much food comes with the meal, and cost of the meal. Each of these considerations can be design variables, constraints, or objectives. If we have plenty of money, then cost can become a design variable. We can choose the cost to meet our taste or size of the meal portions. If we don't have enough money, cost can become a constraint or an objective. For example, when you look at the menu, the cost of the meal must be lower than $10. CA optimization is no different than this kind of daily optimization. Now, let's look at optimization problems for mechanical design. For size optimization, length, position, and angle are typically used as design variables. Minimization of the size or load or performance maximization can be used as objective functions. There are several kinds of limitations or allowable loads that can be used as constraints. For parameter optimization, characteristics of the spring or gains of the controller can be used as design variables. Vibration minimization or performance maximization are typical objectives. Limitation of the spring stiffness or damping can be constraints. For shape optimization, number of links or stiffeners or the 3D shape of a part can be design variables. Minimization of the number of parts or mass minimization can be objectives. Allowable mass or stress can be constraints. This is a typical optimization process. First, formulation of the optimization problem. Second, modeling for the optimization. And third, selection of the optimization method and analysis type. For optimization, we must first list the variables and performance indices. Performance indices are usually the simulation results such as load or stress, velocity, or target position. But sometimes, an input variable also can be a performance index. We classify these variables and performance indices into design variables, objective functions, and constraints. We make mathematical formulations to represent these. Second, modeling for the optimization. For CAE, the variables should be expressed using parametric values. We call it parametric modeling. Most CAE software supports parametric modeling. Be sure to note that mathematical formulations will need to be adapted to the software program you are using. Finally, we should select the optimization method and analysis type that we will be using. For this presentation, we will only be discussing the formulation of the optimization problem. Let's review some reasons why people think optimization is difficult. One reason is formulation. People are confused with design variables, objective functions, and constraints. This does require experience. In this presentation, I hope you can get some ideas about how to classify and formulate variables from the examples that I introduce. Another reason people think optimization is difficult is numerical optimization. There are many kinds of optimization methods and parameters. It is not easy to understand the different optimization options and how to select the appropriate solver. The optimization process inevitably requires iterative simulations. If one simulation takes a long time to run, then running hundreds of iterative simulations can be a large time factor. Also, the different scales of different performance indices can also be a headache with optimization. Fortunately, the latest optimization methods have resolved the difficulties of numerical optimization. So, without a deep understanding of numerical optimization, CAE engineers can still use optimization methods. The options are selected automatically, and the scale difference of the performance indices are normalized automatically. Frankly speaking, I'm not so familiar with optimization theory and details, but I could optimize several multibody dynamics models. All I had to do was formulate the system variables and performance indices. So, as I mentioned, don't be afraid of optimization. Now, let's talk about formulation and modeling of optimization problems. The first step of the optimization process is to list the system information. First, list the design variables. Specify the range of the design variables, the current value, the change cost, and difficulty to change each variable. For example, length or angle can become the design variables. Then, list the performance indices. Some indices are related to economics. For example, minimization of the mass. Others are related to functionality, something like safety or durability. Or maybe there are some regulations to define the upper limit or lower limit of the performance. There can be some limitation for total mass, length, or position. Minimizing the reaction force or applied load is a good example of the performance index. You will also specify the importance of each performance index. Please note that if there are too many design variables, sometimes it is better to exclude some design variables. In this case, it is recommended to exclude the design variables whose change cost or difficulty is high. Of course, if the design variable affects the performance a lot, then it should be included. From the performance index list, we can further classify them into objectives and constraints. First, the performance indices that have apparent conditions or targets are set as constraints. Then, indices whose targets are maximization or minimization are set as objective functions. Since it is recommended to use as few objective functions as possible, you may consider changing some objectives to constraints. For example, instead of minimization, it is possible to use a conditional statement. After deciding the tentative small target value, use the conditional statement as a performance index that is less than the tentative target. It is possible to change the constraints to the objective also. If there is a constraint that has a specific target value, it is possible to set it as an objective to minimize the difference between the performance index and the target value. After formulating the variables, the next step is the optimization modeling. For example, let's assume that we need to optimize the truss model. We should set the positions of the joints or spring characteristics as design variables as shown in this table. After that, in order to use these design variables in CAE software, parametric modeling is used. This means that the design variables such as position or stiffness are expressed using parametric values, and that the performance indices needs to be rewritten in order to be recognized by the CAE software that is being used. This shows how the maximum reaction force and total length are expressed. This is the maximum force among all of the bushings. So I used many max functions. It is used to minimize the maximum reaction force. And this shows how I calculate the total length of the links used for the truss to minimize this. You can use other indices such as operation time or stress by formulating them appropriately. After formulating the variables and parametric modeling, the final step is to optimize the solver setting, such as the DOE method and metamodel method, and other solver options. But this is not covered in this presentation. In this presentation, I used only the automatic option to find the optimal result. I would like to discuss RecurDyn AutoDesign, which is a toolkit used for design optimization. The RecurDyn AutoDesign toolkit is embedded in RecurDyn. It is a general-purpose optimization tool that is very easy to use. The parameters defined using parametric values can be used as design variables, and the expressions are used as performance indices. This page shows the unique characteristics of AutoDesign. The first characteristic is AutoDesign's modeling feature. AutoDesign provides an easy and intuitive interface which allows anyone to use with a little practice, so even beginners can do design optimization. The definition and customization of the design variables and objective functions are easy because it uses parametric values and expressions. All optimization processes are conducted in a single RecurDyn environment, so you don't need to learn how to use other software for optimization. Next are the characteristics of the solver. RecurDyn AutoDesign Solver is the world's first optimization solver that uses progressive metamodel algorithm, which was motivated from Bayesian global optimization. It uses an easy and powerful multi-objective optimization algorithm to find the optimal result, even with multi-objectives. It also supports robust design optimization techniques to consider uncertainties such as tolerances and noises. When each design variable has a different scale, AutoDesign's multi-scale optimization techniques are automatically used to solve the problems, so users don't need to worry about the scales of variables. Various DOE methods and metamodel types are also supported. And if auto option is used, AutoDesign selects the best method and type automatically. AutoDesign, using these unique characteristics, has been used for many projects and has succeeded in getting optimal results with a very small number of trials compared to other optimization tools. For example, a company could get optimal results with only 116 analyses to optimize a design that had 105 design variables and 14 performance indices. Even though this presentation doesn't target the details of optimization method, I think I should take a moment to explain metamodel. Metamodel is also known as an approximation model or surrogate model. In optimization, it is usually called metamodel. As I explained in the previous page, optimization requires many iterative simulations, hundreds and even thousands. It requires a huge amount of simulation time. To reduce this calculation time, many optimization methods will use metamodel. Traditional methods use hundreds of simulations. but MetaModel methods divide the optimization process into inner loop and outer loop. For instance, traditional methods use 200 simulations, but the MetaModel method uses a MetaModel for the inner loop. 20 simulations are performed, and for the outer loop, only 10 simulations are performed. Where calculations using MetaModels are much faster than CAE simulation, the optimization process can become tens or hundreds of times faster. Progressive MetaModel is one of the unique characteristics of AutoDesign. Usually, many simulation runs are needed to create a MetaModel. The conventional MetaModel methods have to use many sampling data whenever updating the MetaModel. For example, let's assume that the optimal result is located on the lower right side of the box, but the user will not know this. So, usually, the initial samples are evenly distributed over the entire area. Using the first MetaModel, the solver may find that the optimal results may exist on the right side. To improve the accuracy, the MetaModel must then be updated. The conventional method will use many samples again in order to update it. Every time the solver updates the MetaModel, many numbers of samplings are needed. Each sampling data requires a simulation run, which means the update will require a lot of calculation time. Progressive MetaModel has a unique algorithm that can reuse the previous MetaModel. Therefore, it only uses one sample. So, after the solver finds the optimal result may exist on the right side, only one new sample of data is needed, which means there is only one simulation to run. And the previous MetaModel is updated using this one additional sample. So, each MetaModel update only requires one more simulation run, which means it requires much less simulation time. In other words, progressive MetaModel can reduce the number of simulations to create the MetaModel. So, the optimization time can become even faster. The first step in using AutoDesign is to list the design variables and performance indices like this. Now, we will take the information from the list and prepare them for the optimization process. Express the design variables using parametric values if you haven't already done so. After that, define the performance indices. Normally, this is done using expressions. However, you can use a scope or processNet function instead of an expression for the performance indices. Now, let's create the design variables and performance indices using RecurDyn AutoDesign. First, create design parameters. They are used as design variables later. You can set the parametric values to each design parameters. After that, create analysis responses using expressions. You can set the parameters for analysis response in this dialog. You can set the appropriate expression in this dialog. For your information, you can use scope, processNet, or flexible body results for analysis response here. Now, you can input the settings for AutoDesign. Create design variables using design parameters that you just created in the previous page. It means parametric values are used for design parameters, and design parameters are used for design variables. Analysis responses are used to create performance indices. It means expressions are used for analysis responses, and analysis responses are used for performance indices. Please note that one analysis response can be used for several performance indices. After that, you need to set the parameters according to the constraint or objective types. After formulating the variables and parametric modeling, the final step is to optimize the solver settings, such as the DOE method and MetaModel method and other solver options. But this is not covered in this presentation. In this presentation, I used only the automatic option to find the optimal result. If you click Execution, AutoDesign Solver will run simulations repeatedly until it finds the optimal result. After AutoDesign solver finds the optimal result, these dialogues are displayed. This shows if the optimal result is found, how many simulation was performed. The optimal result and corresponding design variables and performance indices are also displayed. Of course, you can review the animation and plot for each simulation and of the optimal result. Now, let me introduce the practices to select the design variables and objective functions. The examples shown here are not real models but simplified cases, but I believe they are enough to understand how to choose the variables and objectives. The first example is the truss bridge. It is a common example. This image shows the basic structure, but I believe most of you have come up with an optimal design of this bridge already. The goal is to design a safe and economic truss bridge. Here are the requirements for the design. First, the length of the bridge is 10 meters. This is unchangeable. A concentrated load of 50,000 Newton is applied to the middle of this bridge. The allowable load of each joint is 8,378 Newton. One of the goals of the optimization is to minimize the load applied to each joint. This is related to safety. The limit of the entire length of the links is 46.63 meters. Considering economics, the total length should be minimized. Now, let's list the system information for the bridge. First, the location of each connecting point can be treated as a design variable, and the range of each variable should be defined. Approximately, the range of x direction is set as plus minus 0.3 meters, and the range of y direction is minus 1.5 to plus 0.8 meters. Now, let's list the performance indices. The goal is to minimize the maximum reaction force. As you can see, we have a clear condition for the max reaction force. It must be less than 80,378 newtons. For the total length of the links, it must be shorter than 46.63 meters, and minimizing the total length is another goal. Usually, safety is more important than economics, so max reaction force is more important than the total length. If there are more than two objectives, they require trading off. For example, the optimal length can be 45 when it is the only objective, but it can be 46 when there is another objective. So, if possible, it is recommended to use one objective and use another one as a constraint. So here, only the minimization of the reaction force is used as an objective because it is more important. If minimization of the total length is more important, it is possible to use it as the objective. For this example, the conditional statement for max reaction force and the total length of the links are chosen as constraint. This page shows how the variables and performance indices were input. dp2 is x point of P2 and dp3 is y point of P2. LB means lower bound and UB means upper bound. Since they can be changed, the type is set to variable. For performance indices, AR means analysis response. AR1 is the max reaction force. The max force is calculated over time. The goal is to minimize AR1. AR1 is also used as a constraint. AR2 is the total length. That is the summation of all the links, which must be smaller than 46.63. This shows the optimization process. This animation shows how the optimization solver evaluates the various cases. Please note that the optimization solver doesn't calculate all cases. Instead, it uses the inner loop using MetaModel to reduce the number of simulations and eventually reduces the calculation time. In this model, the number of DOE to create the initial MetaModel was 100, and 6 simulations were performed for optimization to get the optimal solution. If the MetaModel is then used, much more simulation iteration is required. This is the optimization result. The total length of the links of the initial model was 46.63 meters, and the max reaction force was about 111,000 1000 newtons. This is the bridge model that was made manually. The length was about 48 meters and the max reaction force was bigger than 80,000 newtons. And this is the optimization result. The link length of the optimal result is 46.62 meters, which meets the constraint. And the max reaction force was reduced to 79,578 newtons. This is better than the result of the model optimized manually. The truss bridge model can best be optimized with static analysis. However, with this example, I will introduce multibody dynamics models. The goal of this model is to improve the loads applied to the joints of the wheel loader. Please note that this is not a realistic model but a simple toy model, so the load value is not realistic. But it is good enough to be used as an optimization example. In the original model, there are two joints where a much bigger load is being applied to the upper joint here. The design goal is to make the load applied to the upper and lower joints similar. You can see how the wheel loader moves dynamically over time. This arrow means the force vector. Let's see the requirements. The load applied to the bucket is 10,000 newtons. Let's assume that we can change only the stiffness of the upper and lower bushings mounted to the joints. The allowable displacement of each bushing is 0.5 millimeters. In this model, the wheel loader is accelerated for 3 seconds and the bucket is moved by a predefined motion. The two connecting points where the load is calculated are modeled using bushings. The design variables for this model are the stiffness of the bushings. Radial, axial, and rotational stiffness are set as different variables separately. The change cost and difficulty are considered to be the same. The performance indices are the difference of the bushing reaction force and displacements of the bushings. The main goal is making the reaction force similar, so the difference of the reaction forces are set as objectives. The displacements of the bushings are set as constraints and shown as less than 0.5 millimeters. Here, we see how the variables and performance indices were input. Each of stiffness is set as design variable. For performance indices, the third one is the objective function, which is the difference of the reaction forces. It is defined as an absolute value of the magnitudes of upper reaction force minus lower reaction force. The optimization of this model ran 100 analyses. The number of DOE to create the initial meta model was 51, and 49 simulations were performed for optimization. If the meta model was not used, hundreds of simulations for optimization would have been required. This animation shows the difference between the initial design and optimal design. The arrow means the force vector. You can see that the magnitude of the reaction force for each bushing is very similar. The difference is reduced to 1%. Of course, the displacements of the bushings are acceptable. Now, let's fly into the space. The design goal of this model is to design an economical, efficient, fast, and safe solar array deployment system. The requirements is that the solar array should be deployed by only spring damper for the economics of the system. Also, we want all the panels to be deployed simultaneously. In addition, we want the deployment to be completed as soon as possible. For safety, the acceleration of each panel must be less than 0.4 g. In this model, the spring and damper are attached to each joint of panels. The stiffness and damping are the design variables for this system. We will use the acceleration of the end point of each panel as a performance index, and we will measure the time when the speed of each panel becomes 0 to minimize the time to complete the deployment. This is the system information. You can see that the stiffnesses are used as design variables. The stiffness is gradually increased from the starting point to the end point based on engineering experience. It is assumed that all dampers use the same value. The condition will be the settling time difference between each joint as the panels are simultaneously deployed. The main goal of the first index is to minimize it. The second performance index will be the time it takes to complete deployment. This also has a goal to be minimized. The third one is the max acceleration of the end of array, which should be less than 0.4 g. This will be set as a constraint. But to avoid having a multi-objective problem, I chose an appropriate reference value of 0.5 seconds, and I will use the first index as a constraint, where it must be less than 0.5 seconds. The second index will be used as the objective because it is to be minimized. You can see how the stiffness and damping were set as design variables, and constraints and objective functions were set as listed in the previous page. Please note that 0.4 g is shown as 4000. Normally, we would use the simulation results as performance indices. However, settling time is not usually a direct output of CA results. Settling time can be calculated by creating a subroutine. In this model, a C# function was written to calculate the settling time and set it as performance index so that optimization solver could use it. The settling time difference between each joint is also calculated using a C# subroutine. This is the optimization result. The optimization of this model ran 71 analyses. The number of DOE to create the initial meta model was 21, and 50 simulation was performed for optimization. Please see this animation. The settling time difference between each panel met the requirements 0.5 seconds, and the settling time of the entire solar array of the optimal result is reduced from 50 seconds to 8.6 seconds. The max acceleration was reduced to 0.397 g. The next example is the optimization of a hand press. The goal is to reduce worker fatigue by changing the spring position and its preload. The requirement is to minimize the force required to pull the lever, and the press head must be returned to the initial position after operation. This page shows the details of a hand press model. The point where the spring attaches to the gear is variable. The press head must reach to the lower position, and it must return to the initial position after operation. This is the system information. The attachment point of the spring and spring preload are the design variables. The force to pull the lever is set as another design variable. The conditions for the lower and upper position of the press head are expressed as shown in this table. One interesting thing in this model is that the force to pull the lever being used as a design variable is also used as performance index. In other words, it is possible to use one variable for both a design variable and a performance index. Since the press head position is clear requirement, it is set as a constraint, and the force required for operation is set as an objective. You can see the attachment position, preload of the spring, and required force were set as design variables, and the performance index was set as described in the previous page. The optimization of this model ran 57 analyses. The number of DOE to create the initial meta model was 50, and only 7 simulations were performed for optimization. Please see the animation. The stroke of the press head of the new design meets the requirement, and the required force was reduced. The fifth model is a control model. In fact, one of the most frequent use cases of optimization is optimizing the gain value of the controller. In this model, there is a target velocity profile, and we will find the optimal gain to minimize the difference between the target velocity and the actual velocity of the vehicle. This page shows the details of a two-wheeled vehicle, and there are two controllers. The angle and speed difference are input to each controller, and the torque and adjusted posture value are output from each controller and input to the plant model. The gain values for these controllers will be optimized. The design variables are PID of the controller. Please note that the initial design was slightly tuned manually in order to focus on the optimization of the gain values. Only one performance index is used. The velocity difference is the only objective. The safety was not used as a constraint, but if it is needed, for example, the position of the driver can be used as a constraint. You can find that the design variables and the performance index were set as described in the previous page, PID and speed difference to minimize it. The optimization of this model ran 34 analyses. The number of DOE to create the initial meta model was 31, and only 3 simulations were performed for optimization. You can see the change of the gains in PID. This is the initial design and this is the optimized design. And this shows the difference of the initial design and the optimal design. Manual tuning of the gain values is very time consuming, but with the optimization solver, they can be optimized automatically. It is really convenient. It is also possible to optimize the stress using multi-flexible body dynamics, FE-MBD coupling. Here, let me briefly show you how to do this. The connecting rod is a flexible body and the others are rigid bodies. The stress on the flexible body can be used as a performance index. Minimization of the stress over time can be set as an objective. This video shows the optimization process to minimize the stress. With this multi-flexible body dynamics model, the optimization solver finds the optimal result. In this presentation, I have explained that design is the process of making a reasonable choice. Then, I explained that optimization is making the most reasonable choice. The 3 factors of optimization are design variables, objective functions, and constraints. How to formulate the requirements is the key of optimization. Lastly, I introduced various multi-body simulation examples to show how to define the 3 factors of optimization. If you have any question about this presentation or the simulation environment that is used for the multi-body simulation optimization, please send me your comment or click the related links displayed in this presentation page. Thank you for your attention.